Dear students, so we were dealing with the problems related to strain energy method, how to analyze indeterminate beams using strain energy method. So we were using the principle of, that is the theorem of least work, which basically talks about dou U by dou R equal to 0, where U is the strain energy, R is the redundant. Partial differentiation of strain energy with respect to redundant is equal to 0, and we have reconstructed this equation in the form of m dot dx by ei equal to 0 for the convenience of calculation. So if you are having any confusion regarding how we arrived from this to this, just refer back the previous videos. You are going to find the detailed explanation of this reconstruction. Now we are in the last two problems. What we dealt was the case of propped cantilever, which means we are having a fixed support at one end and a prop or a roller was provided at the opposite end. So that's the case of propped cantilever. So now we are going to talk about another major indeterminate structure, and is a common indeterminate structure, which is continuous beam. Okay, so we'll directly jump into a problem. So the problem definition goes something like this. I have a beam, hinge, roller and roller. Okay, let this be 3 meter. Let's put the EI value as constant, and it is subjected to, say, a UDL having intensity 2 kilonewton per meter. So now if you're observing, what is this continuous beam? It's basically, if I have a simply supported beam and in between if I'm providing one roller support, it becomes a continuous beam. Fine. So if I'm removing this beam becomes a simply supported beam, which is a determinate structure. Fine. Now we are going to the first step, that we are going to convert this into a beam of forces. So we are to give we need to remove these figures as a supports, and instead of that we need to substitute those figures with forces. So a hinge can have two reactions, okay, RA and HA. Let this be A, B and C. And here there is a roller which will be providing only one reaction, and this is also a roller, so one reaction, and the load is given as 2 kilonewton per meter. Now we need to decide what is the redundant in this case. To calculate the redundant, the first thing what you need to do is you need to calculate the degree of static indeterminacy. So how to calculate degree of static indeterminacy has already been discussed. So ds is equal to R minus E, where R is the number of unknown reactions and E is the equations of equilibrium. So in this given problem, the value of R is 1, 2, 3 and 4. So there are basically 4 unknown reactions. And as this is a 2D beam, we have 3 equations of equilibrium, that is sigma fx, sigma fy and sigma m. So I'm going to get the value of ds as 1, which basically means that I just need to release one reaction to make this beam a determinate structure. So we have already seen this. If we are removing this particular support, this becomes a simply supported beam, which is a determinate structure. So I'm doing the same. I'm considering this as the redundant. Okay, I'm considering R as the redundant in this particular case. Now we will be going to the construction of table and then the final integration, and we'll be equating it to 0 to get the value of the redundant. So how many segments should be there in this particular problem? Segments depends upon the number of point load locations. Here we have 3 point load locations, hence it will be divided into 2 segments, segment 1 and segment 2. Fine. So we are going to construct the table. So for constructing the table, earlier when we are dealing with propped cantilevers, it was pretty easy. It was pretty straightforward. After this, we'll be directly drawing the table. But when the determinate structure, what we are considering is a simply supported beam, it is not as straightforward. There will be an additional step that comes into the picture. We are going to discuss about that. Okay. So before writing that, I have this equation. I have this beam, right? And we know that if a beam is in static equilibrium, it has to satisfy all the equations of equilibrium. What if I write sigma fx equal to 0 for this particular beam? Whether it is determinate or indeterminate, it should satisfy the equations of equilibrium. So I need some sign convention. I am considering this as a positive one. So there is HA, which is in the direction, so plus. Are there any other forces in the horizontal direction? Nothing is there, which means HA equal to 0. Okay. So now itself I got this value as 0. So for further calculations, I won't be even considering that. I will just ignore it. Now, so what I have is RA, RB, RC. Then there is the load, 2 kilonewton meter. Fine. And we have the distance as 3 meter, which are the span, and EI is constant. Now, how will we be approaching this problem now? We are having two segments. So in each segment, we'll be taking a section and we'll be writing the expression for bending moment. So when we consider a section here, okay, when I consider a section here in segment 1, which side is preferred, left side or right side? If I'm looking to the left, there is one force and one UDL. Right side, one long UDL and two forces. So it's always preferable to look to the left side. So when I write the expression for M looking to the left side, I'm going to have RA in that equation. Okay, reaction RA. When we were dealing with the cantilever problem or the prop cantilever problem, we were always looking to the free end. So when we are looking to the free end, we were not bothered about what the value of RA, HA and MA were. But now it's not the case. We need to know the value of RA. Similarly, when you're taking a section in segment 2, you'll be looking to the right where RC comes into the picture. So first we need to solve the value of RA and RC in terms of RB before calculating the values for the table. So that is the first thing what we are going to do now. Calculating the value of RA and RC in terms of RB and this 2. For that we can use the basic equations of equilibrium. Okay, now what I have is a simply supported beam acted upon by a UDL and a point force. Okay, so the first thing what I'm doing is I'm taking the expression, say sigma MC equal to 0. Let this be A, B and C as we have already named. I'm taking moment with respect to this point. Okay, so what are the different? So here there are a lot of villains, so we'll apply Rajinikanth principle. We are going with RA first. So RA is the force, lever arm is 3 plus 3 because this is a point what we are considering. So lever arm is 6 meter. So the value will be RA times 6. Now I want to know whether it is plus or minus. Okay. So how to know whether it is plus or minus? You use this. This is a point where you are taking the moment. This is the action of force. It rotates clockwise. This is a clockwise rotation. Hence it is plus. Now there is RB. Okay, RB, the lever arm is 3. It causes, okay, RB is here. It causes clockwise rotation. Hence it is also positive. Then what I have is this UDL. What will be the force, magnitude of force? 2 kilonewton per meter. For 1 meter, 2 kilonewton. For 6 meter, 2 into 6. 2 times 6. And what about the point of action of this UDL? It will be at the center, which is basically 6 by 2. What about the sign? This is a point. This is a UDL. It makes it rotate in the anti-clockwise direction. This is anti-clockwise rotation. Hence minus equal to 0. Okay. So from here you can see that this 2 cancels out. So what will be RA? RA is 36. Okay. 6 times 6. I'm taking the right side. So it becomes positive. This becomes negative. Minus RB by 3. Okay. This is 6 RA. So what is RA? RA will be equal to 6 minus 0.5 RB or 6 minus RB by 2. That's the value of RA. Now I want the value of RB. How to get the value of, sorry, not RB. I want to get the value of RC. What about RC? I can use the next equation, sigma Fy equal to 0. So I need some sign convention. I'm considering all the forces in the upward direction as positive. It's my choice. I can also consider it downward as positive. No change. Nothing happens to the problem. Okay. So I'm considering upward as positive. So RA is upward, RB is upward, RC is upward, and this 2 into 6, 2 times 6, that is a UDL, is downward. So minus 2 times 6 equal to 0. So I want the value of RC. So I'm taking all the terms to the right hand side. So 2 times 6, 12 goes to the right, minus RB minus RA. That is 12 minus RB. And what is RA? RA is 6 minus RB by 2. Okay. Which will give me, there is 12, there is minus 6, 6. There is minus RB, okay, and minus RB, minus of minus RB by 2, that is plus. So I'm going to get the value as RC. So now I have the value of RA, I have the value of RC. I'm representing here, this is 6 minus RB by 2. This is also 6 minus RB by 2. So once you have this, then you can think of creating the table. So this is the additional step that is required when we are dealing with simply supported beam. When it was cantilever, there was no worry, no need of all these mess. You can directly start writing the expression, directly start filling the table using the considering the free end, not the end with reactions. Okay, here that option is not there because reactions will definitely come into the picture. So you have to calculate this additional step. And this step is purely based on the equations of equilibrium we learned from engineering mechanics. Sigma Fx, sigma Fy and sigma m. You will be getting the values of reactions. Now we are going to continue from this point. So now it's the part that we are very familiar. We are going to construct the table. So I'm just plotting that beam here again, so that we don't have to refer back every time, each and every time. So this is the beam what we are having, 2 kilonewton per meter, and we calculated this value as 6 minus RB by 2 and this as 6 minus RB by 2. 3 meter and EI is constant. Now I'm going to construct the table. Okay, and we have identified the segments also. We named this as 1 and this as 2. Okay, so the table S, E, L, O, M and M dot. Okay, so that's the content of the table. Let's get that done. So we are going to talk about the segment 1. So when I consider segment 1, I'll be taking a section in segment 1. Now I need to think which should be considered as the origin. Okay, point A, B and C. Which is the preferred one? Definitely A, because if I look to the left side, there are just 2 forces, right side a lot of forces are there, so it's better to look to the left. So I'm keeping origin as A. So what will be the distance x? The distance is from the origin to the section, so this is basically the x. Now we know that the EI is constant. What will be the limit? If A is the origin, the limit of segment 1 will be 0 to 3 meter, right? Segment 1 is up to this point. If this is 0, this is 3. So it is 0 to 3. Now I want to get the expression for moment. Okay, so I'm taking the section here. So what are the forces on the left hand side? One is 6 minus RB by 2 upward and the UDL. So I'm taking one at a time. First I'm calculating this 6 minus RB by 2 effect. So what I will get? 6 minus RB by 2 times X. Okay, 6 minus RB by 2 is the force, X is the lever arm. So multiplying this, I'll be getting the moment. What about the direction? Okay, here what I need to consider, clockwise, anti-clockwise or sagging hogging? Sagging hogging, because it is not summation of moment, it is moment at a point or at a section. So now it is like I'm fixing at this point, and the free end and the other end I'm having a moment like this. So this is sagging, and hence it is this is sagging, and hence it is positive. So I'm not putting plus, it is positive. minus the effect of UDL. So the magnitude is 2 for a distance of x. So the force is 2x. And what about the lever arm? It will be acting at the center, which is x by 2. Okay. So I got the first set of values for segment 1. Now, what is the differential of this? What is this m dot? M dot is basically dou m by dou rb, because here the general equation is dou m by dou r. In this case, r is rb, so dou m by dou rb. So what will this become? What is the partial differential of 6 with respect to rb? It is 0. Then what about this? Minus rb by 2 into x. When I differentiate it, what I will be getting is minus x by 2. Okay. From here, I'm going to get 0. Basically means that minus x by 2. So that's for segment 1. Now I'm going to consider segment 2. So for segment 2, I'm taking a section in segment 2. And which is the preferred side to look for? Left or right? Definitely right, because in the right we have lesser number of forces. So I'm considering C as origin. So the distance from origin to the section is x. I'm taking the moment here. Okay, so I'll fill these details. So C is the origin. So limit of segment 2 is, if this is 0, this is 0 to 3. Okay, this is 0, so 0 to 3. What about the expression for bending moment? 6 minus rb by 2 into x, right? Force times lever arm. Force times lever arm, and it is something like this. So it is sagging. So again, what I'm going to get here is 6 minus rb by 2 times x. And then there is a UDL, and it is going to create a negative moment. So minus, and what will be the value? Magnitude is 2. Distance is x, so 2x is the force. Lever arm will be x by 2, so I'm going to get it as 2x square by 2. And if you're observing, you can find that we got the same expression here as this. Both the expressions are same. So what about here? When I differentiate it with dou m by dou rb, I'm going to get the same expression, that is minus x by 2. So I have filled my table. Now it's simply the integration. So we have the integration. Integral m dot dx by ei equal to 0. So let's substitute. So there are two segments. I'm considering the first segment. The limit is 0 to 3. This is the expression for m, that is 6 minus rb by 2 into x. Okay, into x minus 2 cancels out, x square. That is expression for m. What about m dot? Minus x by 2 dx by ei. What about the second segment? The limit is 0 to 3. Again, 6 minus rb by 2 times x minus x square multiplied by minus x by 2 dx by ei. And we can observe that these two are same. So I can write it as 2 times 0 to 3, right? So 2 times. Now I'm taking the constants out. So I can see here there is an ei and there is a 2 which can be taken out, right? There is a 2 and there is an ei. So when I add these two, I'm going to get 1, 2. I'm taking out the constants, so I'm going to get 1 by 2 ei. Okay? And inside, what will I get? So 0 to 3. I'm taking this, multiplying everything together. So 6x. Okay, this will give 6x, another x. So 6x square minus rb by 2 into x multiplied by x. There is a minus x. Okay, we forgot to put minus here. So minus 6x square, minus of minus become plus rb x into x, that is x square by 2. Okay, x square by 2. Then what? Then we have this minus x square into minus x, that is plus x cube dx. And what should this be equated to? This should be equated to 0, right? This should be equated to 0. So I can take this whole term to the right hand side. It is 0, so this term vanishes. So what I am left with is minus 6 x square. When I integrate this, it's going to become x cubed by 3 in the limit 0 to 3 plus rb x square by 2. Okay, so I put 2 here. Integral x square, it is x cubed by 3 in the limit 0 to 3 plus x raised to 4 by 4 in the limit 0 to 3 equal to 0. Is that fine? Okay, so that's what we got here. Now we can get the value of RB. Okay, when you substitute these values, this is 3 cubed by 3, so this is basically 9. This is again 3 cubed by 3, this is also 9. This is 3 raised to 4 by 4, and when you substitute in a calculator, you are going to get the value of RB as 7.5 kilonewton. Okay, so we have the value of the redundant force RB as 7.5. Okay, now what is left in the problem? We have the value of RB. So how many unknowns were there in this problem? Okay, if we take back the first sheet, the unknowns were RA, HA, RB and RC, out of which the value of HA we found out from here itself. Now we have the value of RB. Now the unknowns are RA and RC. And if you are observing, we already have the equation for RA and RC. Okay, we can use that. So RA is equal to, from here RA is equal to 6 minus RB by 2. Okay, basically means that 6 minus 7.5 divided by 2. Okay, so that is going to be a value 6 minus 7.5 divided by 2. You are going to get it as 2.25 kilonewton. That's the value of RA. And what about RC? RC is also 6 minus RB by 2. 6 minus RB by 2, that is again 6 minus 7.5 by 2, that is also 2.25 kilonewton. Okay, so now we have the values of all the unknown reactions and the analysis is complete. We have the value of RA as 2.25, RC as 2.25 and RB as 7.5 kilonewton. HA is 0, so the analysis is complete. Now what remains is the graphical representation of the shear force diagram and bending moment diagram that you can plot. Thank you.